right, everybody. Hi, welcome to Lithium Pod episode 2. My name is Clay. I'm the founder of Lithium, a layer 1 blockchain and testnet that has a unique consensus we call proof of performance. And we've got some different sort of series we're doing on this channel. This one is the pod, where we sort of just talk about whatever's on our mind or whatever's going on in the industry. And today it's going to be a bit of a deep one. We're talking about this RISCV blog post that Vitalik wrote, where he was suggesting that we could move from EVM to RISCV. And I'm just hoping to explain to everybody why this is being suggested, and also what questions I have about it, actually, which is a lot. And also the Litheum perspective on this, as like, you know, is this a good idea, I guess. Sorry, I just tried to record this once and I'm like losing my voice already, but we're gonna get through this. Yeah, so for those who didn't see, Vitalik wrote this blog. It's been around Twitter. It was called out by Uma here, and then reposted by Vitalik, and then some people have been pointing out that the data from it came from this paper about something called VApps, which is talking about this idea of running the EVM inside a RISC-V based, what would you call it, prover, or, you know, virtual machine, ZKVM. And they use this SP1 specifically, but we'll get into that. So yeah, Vitalik is just saying the idea is to replace the EVM with RISC-V. He's got a chart here that comes from interestingly, he's saying that he believes are the long-term limiting factors to Ethereum L1 scaling. So one is stability of data availability, sampling, and history storage protocols. It's interesting that he says that first, and also I'm a bit confused what he means by stability here. I mean, I would say scalability of data availability, sampling, and history storage protocols, but maybe it's a typo. It kind of doesn't answer the question though, right? Like the limiting factor of scaling is scaling data availability. I mean, that's actually kind of the Lithium point of view. And we see all this kind of stuff as, you know, optimizations that help the scaling, but don't really solve the problem. Anyway, number 2, desire to keep block production at a competitive market and ZK EVM proving capabilities. And he's going to argue that using the RISC-V sort of helps with these number 2 and number 3. I think this is honestly a little bit academic. It'd be surprising if they went this route. It's not a terrible idea, but I'm not really convinced of it through this blog or the paper that I read. But anyway, one point is that, you know, if we say that, where is it? Yeah. If we want a 100x total prover efficiency, there's no getting around the fact that we need to at least 50x EVM prover efficiency. So, I mean, this is assuming that we're going to use ZKs as a way of sending proofs around the network, so that you don't have to necessarily validate an entire block yourself. If you're another validator, you can just get the proof and then confirm the proof or prove the proof or whatever they call it. And then you'd be done at that point. So it would save you some work if you're on the other end. An interesting question though is like, how much more work does the block producer have to make, because they have to produce the proof also. And that wasn't really something that's covered here, but maybe a more interesting concern here is that this is only one slice of what it takes to scale a blockchain, right? I mean, even if 100x total prover efficiency, proving efficiency is only one task of what a blockchain needs to do, right? You still need to get the data, share it with everybody, you know, you've synchronized wallets, right? There's all this other stuff, right? And they're sort of just avoiding talking about that, right? So I'm not even sure that if you could 100x prover efficiency, that you would 100x the scale, or at least like the security of the scale. You could just 100x it if you want, but you'd be compromising the decentralization in a sense by making it more costly for nodes to run. Like just think about you're running a node, an RPC node. You still have to download the whole block. You still have to share all these RPCs with 100 times more wallets, 100 times more, requests for all sort of things from Etherscan to whatever. And then, your prover efficiency is a little bit is optimized, or it's the same as it is today, right? If it's 100x more efficient. Anyway, one thing that we could do is to try to create implementations of the EVM that are much more efficient in terms of prover cycles. Yeah, I mean that seems like the first thing to try. It is being done, and so it's interesting that it's not really being compared here. So I'll show you guys what that means in a moment. So the other thing that we can do is notice that ZK EVM provers today already work by proving over implementations of the EVM compiled down to RISC-V and give smart contract developers access to that RISC-V VM directly. So then he has this data here, which is showing that the proof generation, if you just run natively on your raw hardware versus in a WASM interpreter versus in REVM, an EVM interpreter, then you have this huge cycle count multiplier for generating the proof. Now, we should note what does this mean, right? One thing we could do is to try to create implementations of the EVM that are much more efficient in terms of prover cycles. So this paper, I mean, they're suggesting kind of a whole new architecture for doing this blockchain stuff, which leverages this idea, right? Because you can do it today. I don't know that that's like a great argument, and they haven't really convinced me of that here. I mean, I guess Vitalik found it interesting. They definitely generated some cool data, and it's nice to see, some of this research, but it's not being compared. It's not really a fair comparison in a sense. Some of the more interesting data. So this is the table that Vitalik said was calling out. So this is table 2. We profile Ethereum proving with SP1. So SP1 is a ZKVM that uses RISC-V, right? So zero knowledge virtual machine that proves the correct execution of programs compiled for the RISC-V architecture, right? And you can see this is using RISC-V here. So this is why RISC-V is entering the conversation. And then they ran a couple blocks through this pipeline. So to give you an idea of what's actually happening here and why it maybe is not a super fair comparison, right? We have, this is what's going on, right? You have some Solidity code, could be Rust code, but like Vitalik says in his blog post, that's ugly to write smart contracts in Solidity. But it doesn't matter what language you're writing in, you can compile to any target system, right? So your Solidity can produce EVM bytecode, and then we can take that EVM bytecode, run it on REVM, running on SP1, and then we can prove things. We can create proofs about that execution, and that sort of gives us everything we want, I guess, if we're trying to do this. But like Vitalik said, the other way to do it would be something like this, right? You can, what does he say? Try to create implementations of the EVM that are much more efficient in terms of prover cycles, right? So you can create a ZK EVM, right? And then use that instead. And what the paper is doing is comparing this run versus this run. So they're basically saying, if you compile your smart contract code directly into RISC-V and then run that in SP1 instead natively, it's much more efficient, like 800 times more efficient. And it's sort of like, well, duh, you've got a whole virtual machine extra in here, and it's also EVM, which is not maybe the most efficient thing when you're trying to map it to like 64-bit architecture, right? Because of whatever. We'll get into EVM another time, but there's that. But then, a more fair comparison would be maybe this versus this. And I just wanted to point out that there are really cool stuff. I actually hope people can tell me more about what's going on in this space. especially if there's anyone doing ZK EVM Rust-based implementations. We'd be really interested at Litheum to know about that. I'm not aware of anything that's going on. I asked in the REVM channel. There is no one responded. There are some cool projects that are out there, though. So Soda Labs, I really think they're doing some cool stuff. So they have a GC EVM, which is garbled circuits, which maybe people haven't even heard of. You also have fully homomorphic EVM. I'm forgetting who's building that now, but that's happening. And then you also have Mina, which I really respect these guys. I think they're doing very cool work. They have this really cool graphic here too, which kind of explains what's going on. So, just to go back, like if you want to prove that a transaction is in Bitcoin, people need to talk about this section of the Bitcoin white paper more, because we had proofs before we kind of threw it out. Okay, that's a topic for another conversation. But normally you'd have the chain of all the block headers all the way back to the Genesis block, and then if you've got this block header, you can sort of prove that any transaction is in there because the Merkle root is in there. And the nice thing about proof of work is you also have the difficult hash. So you can just look at the hash, verify the hash instantly by just running it once, and then seeing all those zeros, and you pretty much know it's a Bitcoin block. And so you can trust it even if you get it from like one source, right? Even though you're just talking to like the Bitcoin node that's running on Trezor.io or whatever, you can just, if you get this proof, so this is what they call a Merkle proof, it would be this hash and this hash and this transaction. And the Merkle root, for those who don't know, it's like you have all the transactions in the Merkle tree, and then you hash them, and you hash the hashes in like pairs like this, like hash 2 and hash 3 become hash 2, 3. And then you keep hashing them together in pairs until you get to the root. And then that's that single hash. You can just pass that around. And then anytime somebody wants to prove that a transaction is in that tree, you can send the proof like they're demonstrating here. Hash 01, hash 2, and transaction 3. You can hash all those in the right order together as pairs or whatever, and you'll get the correct root. So this is the data availability program that they're talking about in Ethereum land now. And they're trying to sort of solve this with ZKs. So this whole ZK proof thing kind of has, there's two issues that sort of come into play here. There's the scalability issue, but then there's also the data availability issue. And these are both things that Lithium hopes to tackle in very different ways that are, in our view, critical to solve. I'm going to be talking about this a lot, but if you're on Ethereum and you're, using MetaMask or whatever wallet you're using, you're just connecting to a node, and that node is communicating with your wallet over something called JSON RPC, and you're basically just trusting that that data is correct. We do, in theory, on proof of work systems, have a way of doing this already, but we're sort of in the proof of stake smart contract systems. We're still trying to recover this. And ZK is better, right? And actually that kind of brings us right back to Mina, because what's cool is you don't have to have every block header all the way for all history. You just have this 22 kilobyte proof. And then every time there's like a block, you just generate a new proof, and you can just pass that proof around and you have everything in here. So I think this is, I'm sorry, Mina guys, I don't know if this is EVM. I don't believe it is. But anyway, a very cool project, a little bit under the radar. Not sort of one of the first that comes to mind when you come to the big conferences and everybody's talking about the new hot thing. But from a technical perspective, I think these guys are awesome. And yeah, like I said, Soda Labs too. It'd be interesting to see, this RISC-V SP1 benchmark run against some of those other projects. But anyway, these guys, because you can do it today, like Vitalik said in the blog post, it's like ZK EVM provers today are already working by proving over implementations of EVM compiled down to RISC-V and give smart contract developers access to that RISC-V VM directly, right? So you can do this today. It's not a work in progress. You could in theory, rather than writing a ZK EVM, you could just use this general purpose ZK VM and run the EVM inside it. Kind of an interesting idea, but seems kind of not the most perfect way to do it. I should say, I don't know what ZK EVM, that might be really difficult. I'm not sure if ZK EVM is particularly more difficult than a general purpose RISC-V ZK VM. So, I'm just not that deep into the whole ZK space, but perhaps that's why they don't exist yet. But yeah, that's pretty much everything I think we wanted to say. I do want to point out just, the Litheum perspective on this a bit, which is to say, we're trying to optimize the proving. Oh, one other thing before we move on. They also didn't really break down all the different costs, right? So you've got the normal execution of the EVM, right? And then you just produce the state, and if your state is wrong, like you say, all right, somebody sends person A sends person B 10 Ethereum. Okay, you have to then keep in your EVM state somewhere a thing that says person B has 10 Ethereum, right? If you get that wrong, then in the future, when that person tries to spend that money, you won't be able to validate the blocks properly, and you'll stop participating in consensus. You'll stop earning money, right? So your incentive to correctly interpret the block is created that way, right? Through that future incentive to create blocks or validate blocks correctly in the future. You need to make sure you can maintain the correct EVM state. If you're going to add a prover to that, you're basically, whoever's producing the block still has to run all that code, obviously, but then they produce the proof alongside that. And a big question would be like, how much extra work is that, right? Because if it's like 100 times more work, then that's maybe not. I mean, if you have 1,000 validators and you're saving them 99% of the work, but then the block producer is doing 100 times more work, then in total it's worth doing. But it still seems important to understand that, like, how much more is the validator having to do for producing this proof. Also, somewhere I think Vitalik mentioned that it was like a 1.5 megabyte proof. Whoops. Yeah, maybe that wasn't here. Maybe that was in the paper. But if your blocks are only 30 million gas or whatever, but your proof is like quite large, that could be a problem. Now these guys actually do talk about that a bit, so that you can apparently reduce the size of the proof by converting the Stark into a Snark, and then they're saying these formats are succinct and amenable to on-chain verification. But okay, it would be nice to get some benchmarks on that, right? Kind of the way that they did for these other tables. Oops, I'm scrolling the wrong way. Where we have sort of different cycle counts or whatever for different things they're trying to do here. This is just comparing, by the way, this table just compares the gas versus the cycle count and how those things are mismatched. Vitalik also discusses this issue, and then they say that they want to have the gas cost aligned to the prover. So that would imply that the proving or the production of the proof is more costly than the actual execution of the EVM, right? I mean, the gas cost should reflect the cost that the machine has to incur, right, when it's doing the block production. And so if they're saying the gas cost should reflect the proving cost and not just the execution cost, then that would imply that the proving cost is higher than the execution cost. But okay, that's fine. Even if it's 10x, that's still probably a win, as long as the validation of the proof on the other end is significantly cheaper, which I imagine it was. Plus, you get the win of the data availability, because then you can give that proof to wallets, and then they don't have to trust Infura anymore. So that'd be a big win, obviously. Yeah, and just a little bit of the Litheum perspective on all this. In a lot of our presentations, we like to bring up this slide, right? And so our point of view is sort of that you're focusing on optimizing the thing on the right hand side. So what is this slide, right? This is just to show the mismatch in capital outlays when you have incentives that direct the miners towards one thing, right? You get paid for mining, right? Or you get paid for validation. And so people are willing to buy a lot of Bitmain hardware or stake a lot of Ethereum in order to earn those rewards. But it's seen as a good thing that these so-called full nodes or RPC nodes, in the case of Ethereum, run on cheap little $800 mini PCs, right? This one little NUC boy is from an Ethereum meme where they're saying, you know, who would win in a battle, the global financial system or one little NUC boy? And they're sort of proudly saying that it's good that these RPC costs are limited. And they're not wrong about that, because when you're in this situation where only the block production is incentivized, you have to rely on volunteers to provide these other things. And if you don't, even if you tell the miners like, oh, the miners can provide it, right? It's like a small cost to them, but it's not small if you multiply the size of the block by 100 or 1,000x and the number of people using the chain by, you know, something proportional to that. So, you know, this is sort of why I think Bitcoin and Ethereum are the most well regarded, because they're the most limited and therefore they're the most safe, they're the most decentralized. And, you know, everything that we're talking about here today is sort of trying to help those folks, right? So you're saying, you know, what if the right-hand side of this could be made 100 times more efficient or whatever? You know, that's a bit of a pipe dream, I think, too. And it's really hard to get there. And you have to do radical things like replace the EVM with RISC-V or whatever. But, you know, from Lithium's perspective, this is a little bit silly, because you've got $100 billion of capital. And if you could just kind of redeploy it in a way which doesn't compromise the decentralization, you don't have to worry about squeezing a little bit more performance out of, you know, a $35 Raspberry Pi or an $800 Nuki Boy, or whatever this thing is called, NUC Boy. And so that's sort of our perspective, right? It's like you're squeezing the wrong bottleneck, or you're trying to expand the wrong bottleneck, right? It's, you know, one thing we like to say is that blockchains are intentionally limited, and the bottleneck is unlike the bottlenecks in other chains. And I think there's kind of a recognition of that, in that they are trying to, you know, make this little machine able to do more. But it's really complicated. And wouldn't it be much simpler if we could just have the miners and the validators do the stuff that these other guys are supposed to be doing? That being said, I am very interested to maybe get some kind of a ZK-VM or similar garbled circuit VM maybe into Ethereum, or sorry, into Lithium before we go mainnet. So I'm keeping a close eye on this stuff. So, you know, we may have to try to sneak that in before mainnet, but we sort of see that as secondary to the Lithium thesis, right? Which is that we actually are going to have a problem of like not enough blockchain usage initially, because people are going to have to adopt to this new paradigm that Lithium is opening up, because it's just going to be so much more blockchain available, because you're going to be saying, you're kind of unifying those things, right? You're saying, you know, instead of having $100 billion of hashing and $35 or whatever, we can realistically say that there's maybe 10 to 100,000 Bitcoin full nodes in the world. So we can realistically say it's like maybe $3 million maximum of hardware running these so-called full nodes versus 100 billion doing the hashing. But, you know, with Lithium, we're hoping to align those things, right? So they become one and one. You align the two things, and it just goes faster, and you can just kind of use like a regular old blockchain without and doing any kind of sharding or, you know, requiring too much burden from the dApp developers. Although I don't think using these ZK VM things would be much of a burden on the dApp developers, so long as you have something like the SP1 that just generates the proof for you, and it just up to the consensus to figure all that out, and you can just continue writing Solidity code, and all's good there. So, but yeah, we generally think that EVM isn't as bad as people like to make it out to be, and that really the problem is just that you don't have any incentive to do the EVMing or whatever. And if you fix that, then all these problems sort of go away. So anyway, that's all for today. I hope that was helpful for people. Like I said, I still have some questions myself, but I hope that I at least was able to sort of give some clarity on like why people are talking about this and what the impact would be for Ethereum. If you want to check out Litheum, we've got press releases going out really soon, which should maybe be interesting to people. We've got the builders program. We're trying to get it out as soon as possible, but it's like you just want to get everything right. We're hoping to have it out early next week. So yeah, subscribe to the channel, subscribe to our Twitter. Twitter is probably the best place if you want to follow along. And yeah, if you've got a cool dApp idea, definitely let us know. This era is all about sort of explaining to dApp developers what makes Litheum different and why we think it is the best ecosystem in the long run for you to be in. It's EVM compatible, so not like too much of a burden to just deploy. You just a little bit of hard hat config and an extra couple, commands on the command line, and you're on our test net. And so yeah, we're targeting mainnet. Hopefully this year. Well, definitely this year will be feature parity or feature complete for a mainnet, but we'll see how things go strategically, depending on the market, also depending on what we want to get in, because I really do want to also try to sneak in some of this ZK garbled circuit stuff maybe before mainnet, because it would be more trouble to do it post mainnet. But it also depends how much traction we're getting. And then also we ultimately do need to write our own wallet too. So because the JSON RPC interface that wallets use to talk to EVM compatible chains now doesn't support the things we want to do as far as like solving some of these data availability problems. So, and also there's a feature we have called lucky hashing where everybody's sort of automatically staked. And if you just hold some Lithium in a wallet, you're always earning a little bit and you're participating in the consensus. We're going to talk about that a lot more in the next phase of our testnet. But right now we're just focused on the EVM compatibility and the dApp developers. But yeah, anyway, hope this wasn't too long. Thanks for hanging in there, and we'll see you in the next one. Bye.